session.
I hope yesterday was a good start. We had good talks and nice discussions as well. So today Professor Yuri Luchko will continue his lecture, and so we the name of the lecture. Yeah. So you can continue, and you have consecutive to lectures. We will have a break, 15-minute break at 11:15. So welcome.
So thank you very much. Hello everybody. Today we continue my talk. And as you remember, yesterday I already introduced a special set of the Sonian kernels and the so-called general fractional integrals and derivatives with these kernels. And today we continue with some generalizations of these operators and the Sonian condition, and then I'll show you some applications of the theory, including the so-called generalized convolution Taylor formula and series, and then we consider some simple fractional differential equations with these operators. Well, let's start with the first generalization. As you remember, yesterday the operators that were introduced, in particular the fractional derivative, introduced yesterday has a generalized order between 0 and 1. It means that in the second fundamental theorem we have just one initial condition. And in the case one is going to apply these operators, for example, to construct more general models for wave diffusion-like equations. Of course, an operator with the order between 1 and 2 is needed. And how to introduce this operator? It's very easy thing. So let's consider this this generalized Sonian condition and introduce a pair of the pairs of the functions kappa and k, such that their convolution is not just one, not the constant one, but the n-fold convolution of the constant function 1. So with this symbol, the n-fold convolution is denoted. It's of course not power function, but this n-fold convolution. And the n-fold convolution of 1, it's very easy to calculate, is just the function hn. This power function, t to the power n minus 1 divided by n minus 1 factorial. It's our basic power function. And we continue to consider the kernels that with the properties that the first kernel, kappa, is from the space C minus 1. It means that this kernel can have singularity at the origin or not. I mean, this space consists of functions that are represented as a product of power law function with the exponent greater than minus 1 multiplied with a continuous function. And the second kernel, this kernel k, is from the space C minus 1, 0. That means that this kernel has to have a singularity at the origin, because the space consists of all functions that are represented as a power law function with the exponent between minus 1 and 0 multiplied by a continuous function. That means that these kernels, they have integral singularity. So you see that these pairs, kappa and k, are ordered. Yeah? So we cannot just change the order of the kernels because they belong to different spaces. And of course, in the case of the standard Riemann-Liouville fractional integrals and Riemann-Liouville fractional derivatives, these conditions are fulfilled, yeah? Because they also are defined for arbitrary order alpha, and the Riemann-Liouville fractional integral, the kernel of the Riemann-Liouville fractional integral can be singular in the case alpha is between 0 and 1 or not. In the case alpha is greater than 1. But the kernel of the fractional derivative is always singular. Well, having introduced the space of the kernels, does it work?
Okay. You can click, yeah.
And
it is stopped.
Somehow.
Let me advance the battery.
Okay. Well, how to construct the kernels from Ln? The kernels that possess this property that fulfill the generalized Stonian condition. For example, we can construct them as follows. If we take the kernels kappa and k from the set L1, these are just normal Stonian kernels, and consider the n-fold convolutions, then of course the convolution of these both kernels is just the n-fold convolution of the convolution kappa and k that is equal to 1, because these kernels belong to the space L1, and thus the kernels kappa n and kappa kn belongs to the set Ln. But of course we have to ensure that the kernel k n-fold convolution of k belongs to this space, because it's not automatically the case. Another possibility is to take two kernels from L1 and to construct a convolution of the first kernel with the function with the n-fold convolution of the function 1. It's of course a power law function, and in fact it's nothing else as the n-1 fold integral of the function kappa. In this case, both conditions are fulfilled. So this pair of the kernels always belongs to the set Ln. And there are some other possibilities to construct these kernels, and in particular in this paper by Tarasov, Generalized Fractional Calculus, Multi-Kernel Approach, he suggested some other constructions for the kernels from Ln that are built by using different kernels. Doesn't work. So now I would like to present some open problems. For example, to characterize the space of functions C minus 1k, 1. It consists of all functions from the space C minus 1 with the property that the general fractional derivative with the kernel k of the Riemann-Liouville type is also from the space C minus 1. It's a generalized version of the space of continuously differentiable functions, but of course not exactly. How to characterize the space of functions. Of course, we can say that the functions in the form general fractional integral of a function phi at the point t with a function phi from the space C minus 1 belongs to this space. Yeah? So the functions that are represented as fractional integrals of course belongs to the space, because if we calculate the derivative here, then it's just the first order derivative or the nth order derivative that it doesn't play. Okay, we take the nth. I didn't introduce it. No. Just a moment. Oh, I think I formulated this the first problem a little bit early because I didn't introduce yet the fractional derivative of arbitrary order, but we restrict ourselves to the case of the kernels here, kappa and k from L1. Then the fractional derivative has this form, and if f can be represented as a fractional integral with the kernel kappa, then we have here a composition of two integrals, and these integrals are nothing else as convolutions. Here we can just build the convolution of the kernels k, kappa, and phi, and the convolution k and kappa is just the constant function 1, because these kernels, they fulfill the Sonian condition, and then we have here the convolution of the constant function 1 with the function f, and it's of course definite integral. And then we just use the fundamental theorem of calculus and get the function phi. That is from the space c minus 1. That means that the functions that are represented in form of the fractional integrals, they belong to the space of function, but of course some other functions too. Another open problem is to determine the conditions that a function from the space c minus 1 should fulfill to be from the set L1. I mean, this problem is just equivalent to the problem to solve an integral equation of this kind, convolution integral equation, with the constant function 1. So it means that taking a function k, for example, we try to solve this integral equation at least to show the existence of a solution to this equation from this special space of functions. And if the solution exists, then it's unique because of the Titchmarsh theorem, but still the problem is how to determine this solution. Of course, it's not a new problem. What is new here, or difficult, is of course the space of functions, because Sonian solved this problem in the special case when the functions are represented in form of power law functions multiplied with some analytical functions, yeah? With some analytical functions, not continuous. In this case, Sonian could solve the problem because he could determine the second kernel kappa and the coefficients of the corresponding analytical function. The same problem, of course, for the kernels from the space Ln that satisfy this more general condition. It's an integral equation, and of course could be interesting to study this question. Well, later on I will formulate some other open problems.
Professor,
And
let me try to fix this.
having defined the generalized Stoning condition, the so-called general fractional integrals and derivatives can be defined in a standard way. So the general fractional integral is defined as before in the same form with the kernel kappa, and the general fractional derivatives of the Riemann-Liouville and Caputo types are defined in more general form with the nth derivative, and the kernels k and kappa, they belong to this space Ln of kernels. And this fractional derivative of the Caputo type is a regularization, suitable regularization of the general fractional derivative of the Riemann-Liouville type. So you see here practically the same form as it is the case for the standard Riemann-Liouville and Caputo fractional derivatives. Even the sum is the same, and it's not occasionally, we will say later on, that this term, the form of this term follows from the second fundamental theorem for the general fractional integrals and derivatives of the arbitrary order. Okay. Well, here are some examples of the suitable kernels. Of course, the case of the Riemann-Liouville and Caputo derivatives is included. In this case, the kernel kappa is just the function h alpha, the power law function, and the function k depends on the value of alpha. Alpha is between 1 minus n minus 1 and n, and is a natural number. Then the kernel k is the kernel h n minus alpha. N minus alpha is between 0 and minus 1, so it's a singular kernel. And then we get here just the standard Riemann-Liouville fractional integral and Riemann-Liouville fractional derivatives. Of course, for other kernels of this kind, one can construct different operators. And in a certain sense, these operators are not better, but also not worse than the standard Riemann-Liouville fractional integrals and derivatives. For example, if we take the kernels or modified version of the kernels introduced by Sonin in terms of the Bessel function j and the modified Bessel function I with some power law multipliers, so it's an easy exercise to check that these kernels, they belong to the set Ln of the kernels, and then the general fractional integral can be written down in this form with the Bessel function here, and of course power law function, and the general fractional derivatives, they take this form. This is the form of the Riemann-Liouville type fractional derivative, of course modified with the modified Bessel function in the kernel, and this is the Caputo version. And we will see that some basic properties of the fractional integrals and derivatives are fulfilled, automatically fulfilled for these operators. Well, there are also many other cases, many other new and known cases of the kernels. What can be shown for this general fractional integrals and derivatives of arbitrary order? Again, for the general fractional integral, we have the same properties. Mapping property in the on the space C minus 1. Commutativity law, of course, and the index law in the same form. So if we take a composition of two operators, then we get an operator with the kernel that is a convolution of the kernels kappa 1 and kappa 2. Practically by definition, this index law follows. As to the fractional derivatives, general fractional derivatives of the arbitrary order, again, the two fundamental theorems of fractional calculus or calculus are fulfilled here on the special spaces of functions. So the fractional derivative with the kernel k of arbitrary order. In this case, the kernels kappa and k are from the set of kernels Ln. And both derivatives of the Riemann-Liouville type and of the Caputo type are left inverse operators to the general fractional integral on special spaces of functions that we introduced yesterday, c minus 1 here, and here c minus 1k. Oh, the first fundamental theorem is there, and the second fundamental theorem is the form of the second fundamental theorem is more complicated, again because we consider the operators of arbitrary order. The derivations, by the way, the derivations of these formulas are very technical. Yeah, it's nothing. They are not complicated, and therefore I decided to save time and just to present some results and ideas. And for the details, for derivations, for the proofs, please look at this paper. So the proofs are there. Nothing special, standard proofs. And you see here that this composition is practical identity operator, but with some additional terms. And the form of these additional terms determines, in fact, the natural form of the initial conditions while dealing with the fractional differential equation with this operator. So the initial conditions are like in the case of the Caputo fractional derivative, so they're just integer order derivatives of the function f at the point 0. And here we work on the space c minus 1n, the space of the functions with the property that the nth derivative of f belongs to the space c minus 1. In the case of the Riemann-Liouville general fractional derivative of the Riemann-Liouville type of arbitrary order, the formula is a little bit complicated. So here we take again a pair of the kernels from Ln, and under additional conditions that the kernel kappa also belongs to the space c minus 1 and minus 1. And then for the functions whose fractional derivative for with the kernel k belongs to the space c minus 1, the following formula is valid. Yeah? You see here that this sum, the form of this sum is a little bit complicated. So here we have the form of the natural conditions. In fact, you see here, as is the case of the Riemann-Liouville fractional derivative, we have to build integer order derivatives applied to this integral with the kernel k evaluated at the point 0, and the functions, this additional terms, they are built by derivation of the kernel kappa. Of course, in the case of the kernels kappa and k that I already showed you, Paolo kernels, we get here the Riemann-Liouville fractional derivative and the Riemann-Liouville fractional integral, and of course this formula is well known. So this formula is well known, but of course in the case of the general kernels it's a new formula and important one. Yeah? So we said here we have the form of the natural initial conditions. Well, having defined the integrals, general fractional integrals and derivatives of arbitrary order, we consider now another generalization and introduced the so-called n-fold general fractional integrals. These are repeated integrals, and also n-fold general fractional derivatives. And applies them for example, derivation of a new version of the Taylor formula, or the formula of the Taylor type. As to the n-fold general fractional integral, its definition is a standard one, nothing new. It's just repeated integral, but by employing the index law, we can represent this repeated integral, this composition, just as a convolution. It's nothing else as the n-fold convolution of the kernel kappa here. Yeah? And this operator is nothing else as the general fractional integral with the kernel n-fold convolution of kappa. So you see here that the n-fold integration, n-fold integral is reduced just to one integral, as in the case of the standard integrals. Also, this formula is well known. So here we don't get something new. But then we introduce the so-called n-fold general fractional derivatives of the Caputo type and of the Riemann-Liouville type. And in this case, we have here a composition of integrals and derivatives. And of course, in general, we cannot interchange the order of the derivatives and integrals, and these are practically new objects. For the sake of simplicity, let us restrict ourselves to the case of the kernels from L1. So they satisfy the normal Sonin condition. Of course, the whole theory can be developed for the case of the kernels from Ln, so for the case of the derivatives of the arbitrary order. And now we deal with these operators just in the standard way. And again, two fundamental theorems can be proved, can be derived, also without big problems, just by considering these objects and with some standard manipulation, nothing special. And again, this repeated sequential fractional derivatives are left inverse operators to the n-fold fractional integral, of course, on the special spaces of functions, as we expect. And the form of the second fundamental theorem determines the form of the initial conditions by dealing with, for example, multi-term fractional differential equations with these operators. And you see here that in the case of the Riemann-Liouville type fractional derivative, general fractional derivative, or sequential fractional derivative, this composition is the function f with some additional terms. And the form of these additional terms determines the form of the initial conditions. You see here that we have here a very special interesting object here, convolution of the kernel K with the sequential fractional derivative of J-fold sequential fractional derivative. And this convolution is, of course, nothing else as the fractional integral with the kernel K. And we have here a sum, and the terms of the sum are J plus 1 fold convolutions of the kernel kappa. And if we take a closer look at this formula, then of course we can proceed like in the standard case of the Taylor formula for the function that is n times continuously differentiable. So one of the possibilities to derive this formula is just to consider the n-fold integral applied to the n-fold derivative, and then we have similar formula. Of course, here we have just normal derivatives evaluated at the point 0, and here we have power law functions. And then look, we can now represent the function f of t in the form of this object, and I called this object convolution polynomial because it's nothing else as a far-reaching generalization of the power law series. In the case of the power law series, this kernel kappa is nothing else than the constant function 1. And we have here just power law functions, t to the power n j divided by j factorial. But in general case, we have this convolution polynomial. So if we move this sum to the left-hand side, then we get a representation of the function f of t that belongs to the space of function in form of a convolution polynomial. And this is nothing else as the so-called Taylor type formula for the general fractional derivatives in the Riemann-Liouville sense. So we can represent the results shown on the previous slide in this form. So for any function f from the space of function, we can derive this representation, Taylor convolution formula, with a convolution polynomial, and the coefficients a, g, j can be calculated in terms of the function f, of course, through this general fractional derivatives. These are these objects, and the remainder term is nothing else than this object. It's a composition of the n-fold integral and sequential derivative, and here we can use the fact that this integral can be represented just as one-fold integral with the kernel kappa, the n-fold convolution of kappa, and then we can use the mean value theorem for the integrals and get this representation. It's something like a remainder in the form of Lagrange. Yeah? If you project this result to the case of the normal polynomial. Now, well, having derived this formula, I asked myself regarding Taylor series. I mean, here we have Taylor polynomials, but in the calculus, one speaks about so-called Taylor series that converge under certain conditions to the functions that we like to represent in form of power series, and there is a formula for the coefficients of this series and so on. Of course, the same play can be done here. Oh, we can pose and solve the question regarding convolutional Taylor series, but first I would like to show you an example of this formula, generalized convolution Taylor formula, for the Riemann-Liouville derivative. Yeah? In this case, this kernel kappa is just power law function, and this formula takes the form of the Taylor polynomial is still a power law function, but of course with non-integer exponents, and the coefficients can be calculated in terms of the sequential Riemann-Liouville derivatives, and here we have to apply the Riemann-Liouville integral of the order 1 minus alpha. and the remainder takes this form. In fact, some years ago, in fact many years ago already, there were some publications devoted to the versions of the Taylor formula for the fractional derivatives, and formulas of this kind were derived already. It's not a new formula, but of course taking this generalized version and taking other kernels from the space L1, of course we get some new representations. That would be probably useful. So then we shortly discuss the same play for the Caputo type fractional derivative. For the Caputo type fractional derivative, sequential derivative, the second fundamental theorem looks differently. You see here that we get the term f of 0 and then some convolutional terms. This difference is very essential, in fact, because on the space C minus 1n, these convolutions are continuous functions. So in this case, this representation is a convolutional Taylor polynomial will be valid just for continuous functions, f of t, because this term is continuous. In the case of the formula for the Riemann-Liouville fractional derivative, look here, we have here this sum, and if j is equal to 0, then we just have here the function kappa, and the function kappa is not continuous everywhere. It's singular at the origin. So this formula is valid for representations of functions that can have integral singularities of the power law type at the origin. But another formula, this formula with the Caputo fractional derivative, is valid just for continuous functions. Well, of course, you see here that we have different coefficients, but also different basic functions here in the polynomial. And from this version of the second fundamental theorem, of course, similar generalized convolution Taylor formula can be derived. It looks differently, and in fact, even these basis functions are different. Yeah, because here we have integrals of the j-fold convolutions of the function kappa, and in the previous formula we had the g plus 1 fold convolutions of the function kappa, so that are different functions. We will see later on some examples of this kind of series, and you will see that these representations are completely different, in fact. Yeah? And here we also can derive the form of the remainder in the form of Lagrange by the mean value theorem, no problem. And of course, we again got maybe potentially useful representation of some functions in form of the convolution series. Oh, and in the case of the power law kernel H alpha, we get here the Caputo fractional derivative, and the generalized Taylor formula for the Caputo fractional derivative looks like this. So the function, any function f of t, not any, but of course from certain space of functions, can be represented in this form. You see here again the term f of 0, the initial term, the form of the first initial condition for the fractional differential equations with the Caputo derivative. And here we have sequential Caputo type Caputo derivatives evaluated at the point 0. And the basis functions are power law functions. And the form of the remainder is like this. This is more or less new formula because earlier some people consider it, as I already said, this kind of formulas for the Riemann-Liouville fractional derivative, but not for the Caputo fractional derivative. Well, some open problems I have formulated here. There are many because these objects are more or less new. Well, as I already explained yesterday, they are simultaneously old and new. So the first contributions were made about 200 years ago, first by Abel and then by Sonin. But after that, only few research was made in this field. But starting from the publication by Pochubey, I mentioned yesterday, in 2011, so some people started to work with these objects, and therefore the theory is more or less new. So, theory of the n-fold general fractional integrals and the sequential general fractional derivatives of arbitrary order is not yet developed. I consider it just the case of the kernels from L1, and also the form of the generalized convolution Taylor formula for this derivatives of arbitrary order is also not here. Yeah? So just consider the case of the kernels from L1. You have seen the formulas are complicated enough. Yeah? But if you consider now sequential fractional derivatives of arbitrary order, then of course all this stuff will get even more complicated form. So even more complicated form, but maybe useful. Yeah, who knows? Who knows? Well, having derived the Taylor formulas, now let's consider the so-called convolution series. As I already said, it's a far-reaching generalization of the power law series, and power series are everywhere. Yeah, you know that they are used in analysis, in differential equations, in applied mathematics, in numerical methods, everywhere. And here we have a useful, I think, generalization of the power law series, so-called convolution series. So if we can take the kernels not from L1, so we can neglect the Sonin condition. We just take any function from C1 that is represented in the form of the power law function multiplied with by a continuous function. And if we suppose that this standard power series is convergent in any point not equal to 0, so the convergent radius is not equal to 0, then it's not difficult to prove that the convolution series of this form with the same coefficients, but with the n-fold, with the j plus 1-fold convolutions of the function kappa, is convergent one for all t greater than 0, and this sum belongs to the space C minus 1. Moreover, if we multiply this series, the sum with the power function t to the power 1 minus alpha, where alpha is minimum from p and 1, then we get uniformly convergent series on any closed interval. That means that we can work with this object. We can integrate this object term by term. We can differentiate the object, the series term by term. So everything is possible. Well, And this series, this convolution series can be used, as I already said, for different aims. For example, I tried to use the series method to solve some fractional differential equations. As you probably know, power series are useful for deriving explicit form of solutions to some important differential equations. For example, of the second order, for example, the Bessel differential equation. Now, the solution can be derived in form of power law series by standard methods. And the idea behind this power series method is very simple, because if you have standard power law function t to the power n minus 1, it's a function that we define that we denoted by hn of t. Of course, you remember that these functions are used in the Taylor formula for the functions, and their most important property, or one of the most important property, is as follows. If we calculate the derivative of this function, then we automatically get the function of the same form. This is just hn minus 1. And this is the property that is used by using the power series method for solving differential equations. And in the case of this series, of course, the most important property is as follows. If we apply the general fractional derivative with the kernel k to this term, to this convolution, j plus 1 fold convolution of the function kappa, then we have this exactly the same plane, because here this operator is just the first order derivative applied to the general fractional derivative is the kernel k, and then we apply everything to this function, and then we have here just a convolution of k with kappa j plus 1 convolution, and then we use the Sonic condition. Of course, in the case later on, this result is valid for any convolution series with any function kappa from c minus 1. But of course, useful results will be derived in the case of the kernels kappa and k that satisfies the Sonic condition. Later on, we will consider this class of kernels. And then, in this case, the convolution of k with kappa is just 1. It's definite integral. So derivative applied to the integral is the function, and what is left is just one function disappear here, because we consider the convolution k and kappa, and what is left is just the j-fold convolution of kappa. Yeah? So behind this machinery is we have this consideration. So in fact, as we already said, this function t to the power n minus 1 can be interpreted as the n-fold convolution of the function of of the constant function 1. And then this derivative is the n minus 1 convolution of the constant function 1. And so we have here a very, very particular result. These are very huge objects, by the way, this convolutional series. At least I could not find any publications, any earlier publications devoted to this sort of, in fact, special functions. These are new special functions or new form of the special functions. And one of the most important objects of this kind is generated by the geometric series. Yeah? It's clear, geometric series is one of the most important objects in analysis and maybe in the whole mathematics. And of course, it's not this convergent series. And if we replace this power law function with the convolution, then we get this special convolution series that I denoted with L kappa lambda, and this series is convergent for all t and is a function from the space C minus 1, 0 plus infinity. And of course, it's not a surprise, or it will be not a surprise, that this function plays a very important role by considering fractional differential equations. These operators. And let us consider some particular cases. What happens if we take the constant function 1 as the kernel kappa? Then we have already seen that we can calculate the j plus 1 convolution of this function, and it's just a power law function. So this series then is nothing else as the exponential function, e to the power lambda t. One of the approaches to introduce all functions, not just elementary functions, is in the framework of series. Yeah? Probably some of you know that my PhD advisor, Professor Marichev, is working for the computer algebra system company Wolfram Mathematica for many years already, more than 30 years. And there he was in particular responsible for realization of algorithms for working with special functions. And of course, one of the problems, what is a function? How can we save the function in the framework of a computer algebra system? What is it? And finally, he tried several approaches, and finally he decided, or maybe not decided, but he went to the idea that the most useful and probably general approach to define function is through Taylor series, through the power series. And this definition of the exponential function is more or less a basic one. Well, what happens if we consider other kernels? For example, this power law kernel, H alpha, is the kernel of the Riemann-Liouville fractional integral. In this case, it's also very easy to calculate this j plus 1 fold convolution in explicit form. It's again a power law function, and this convolution series takes the form well known in the theory of fractional differential equations. This so-called Mittag-Leffler function with two indexes, alpha and alpha, and with the power law function. And this function is, of course, basic in the theory of ordinary differential equations. fractional differential equations with the Riemann-Liouville fractional derivatives. Of course, it's clear why, because it plays the role of this exponent function in this sense. Taking other kernels, we get another representations and so on and so on. I derived several new representations, several new functions here in terms of the, for example, multivariate Mitter-Clippier function and so on. Now, well, let's speak a bit about the so-called convolution series. As we already said, in the Taylor formula, we get some convolution polynomials. Let's discuss a question about the series. So let's start with the problem that we have a function f from the space C minus 1. And we suppose that this function is represented in this form as a convolution series. How to determine the coefficients? Coefficients AG. Well, in fact, we already answered this question more or less, because we already derived the Taylor formula, and if we let n go to infinity in the Taylor formula, then of course we get this Taylor series, and the answer to this question is more or less clear, but of course it should be justified, proved in explicit form. So in this recent paper published in the journal Fractional Calculus and Applied Analysis, I dealt with all these questions, and in particular for any function f in the form of convolution series with a Sonian kernel from this class L1, this function can be represented as the following generalized convolution Taylor series. So you see that we have here the same coefficients as in the case of the Taylor formula, and we have here the j plus 1 fold convolutions of the function kappa, and kappa is the kernel of the corresponding general fractional integral. So the Taylor series, of course, that we all know from analysis is a very particular case of this formula, and in the case of the Caputo type fractional derivatives, we can use also the same machinery and get another representation. Yeah? You see here that what is here is not exactly a convolution series, because we have here not these basis functions like in this case. Here we have exactly this j plus 1 fold convolutions. So I would say that this is a classical convolution series, and this one is a modification. Yeah? In this case, in this sense, we can say that the general fractional derivative of Caputo type is not suitable for dealing with generalized convolution series. Yeah? But the Riemann-Liouville form of the general fractional derivative is more suitable. Well, this was one aspect, and having introduced this convolution series, of course we can speak about many applications. And the first one, as I already mentioned, is to try to use this series to derive some solutions to some differential equations with the corresponding operators, with the general fractional derivatives. Just in the same way as we use the power law series to derive analytical solutions to the, for example, Bessel differential equation. So the coefficients can be constant or can be polynomial, yeah? Even in this case. And of course, the first result that has to be proven here and already proved in this paper, also recent paper, is the following one. We have to guarantee uniqueness of of this new object of this convolution series. And indeed, it's not difficult to show in exactly the same way as for the standard power law functions that in the case two convolution series coincide for all values of t, then it's the case then and only then if the corresponding coefficients are equal. So this theorem opens the gate to applications of these objects because these representations are unique. And then if we consider fractional differential equations, for example, let's consider this simple, very simple fractional differential equation, so-called relaxation equation with the general fractional derivative with the kernel k. And if we suppose that the solution can be represented in form of this power law function of this convolution series, and in the case we are looking for solutions in the space C-1, then of course it's reasonable hypothesis that this representation is valid, because we showed that that any function from C1 can be represented in this form. And then we proceed very clear. We substitute this representation into the equation. Then we use the properties of the convolution series, and in particular we can apply the derivative term by term. And then we can use this relation that the derivative of the j plus 1 fold convolution is the j fold convolution. And then we can just compare these two series on the left hand side and on the right hand side. And as a result of this procedure, we get some equations for the coefficients, unknown coefficients, and we can solve this equation term by term, and the analytical solution, as you see, is expressed in terms of the special convolution series. Of course, it's not a surprise, it's an expected result, because this series is generated by the geometric series that is reciprocal to a fraction somehow. In the next lecture, I'll show you some elements of the so-called operational calculus for these operators, and you will see how this machinery works. And then we get this result from it. Of course, the same procedure can be applied for more complicated equations and so on and so on. But let us make a break and drink a cup of water and coffee, and then we continue in 15 minutes.
Yeah, thank you very much. Any questions, remarks? If there is no, okay, Professor Sladicka.
I have a question about the computational aspects. Do you have any experience about this? Because you are using here, let's say, constant lambda, and if you can apply this to some PDEs also, because then you are allowed to use this series, to use it for another basis and go with this. And the question is, once you take into account fractional differential PDE, then you have some integrals, and what about the computational aspects about this?
It's a question that it is not exactly in my field of research, but as far as I know, nobody investigated the computational aspects of the smallest new objects. There are some theoretical papers regarding existence and uniqueness of solution of certain initial value problems, initial boundary value problems for the partial differential equations with this new object, with these derivatives. So it's provided, but I am not aware of any papers with numerical aspects, with computational aspects.
but I'm afraid that it will take a lot of CPU.
Probably, yeah. And of course, before you start with computer simulations, of course, the question if these equations are suitable for modeling of something is important. But yesterday, while speaking about the results by Kochubey, I stress this aspect because Kochubey considered the Cauchy problem for equation of this type with this general derivative with the kernel k and with the Laplace operator here in the multi-dimensional case, and he showed that the fundamental solution of this equation can be interpreted as probability density function, and it's already a very good sign for applications because the generalized order of this equation is between 0 and 1. So this equation could describe some, for example, anomalous diffusion processes. But of course, to be realistic, the interpretation as a probability density function is required. So you have to guarantee the positivity of the quantity, yeah? And this result is there. Yeah? Of course, this result is theoretical one, and to justify that objects of this kind are useful for applications, of course, you need some concrete processes, some data, you need to prove all these things. It's not so easy. But at least theoretically, at the moment, we have no obstacles for applications of the equations of this kind. Okay. And there are even some publications regarding inverse problems for equations of this kind. For example, Professor Yano, well-known expert in inverse problems, published something, Umarov, Sabir Umarov, and Yamamoto, and so on. It's another aspect. I mean, having a model in this form and some data, how to determine this kernel, K, for example. Yeah, it's of course the most basic question in applications. Yeah, because of course it's not possible to derive equations of this kind from the first principles. Even in the case of the standard Riemann-Liouville derivatives or Caputo derivatives, it's not possible. And the only way to somehow to use these models is to determine these kernels or orders from the measurements data. And, that means that you need to solve some inverse problems in this sense. But it's another topic, of course, yeah. Very important, I agree with you, very important topic regarding applications of this object, but also very complicated, yeah. So, thank you.
Okay, any other questions? If no, we will have a 15 minutes break. You can go to the kitchen and get some coffee. And we will be back in 15 minutes.